Today I want to remind you how bijective proofs work. We said last time that 1 plus z to the n is a sum of n choose k, as k goes from 0 to n, z to the k. So if we plug in z equals 1, I guess that means that 2 to the n equals a sum of n choose k. That is, the total number of subsets of a set, including the empty set, is 2 to the n. The number of subsets of an n-element set is 2 to the n. So one proof is we plug in z equals 1 in this equation, but I want to show you a bijective proof. We start with the left-hand side. 2 to the n is the number of binary words of length n, b1 through bn, where bi is 0 or 1. Now each such word has ones in some of the positions. Let's say I1 through IK. Then I1 through IK is a subset of 1 through n. So by making the binary words line up exactly with the subsets of n, we can see that, well, any two sets that where the elements line up perfectly are in bijection, so there's the same number of them. All right, now let's look at some similar statements. I claim that the number of odd cardinality subsets of n equals the number of even cardinality subsets. Now clearly the number of subsets containing n, the number n, equals the number of subsets not containing n. And to see how they line up, if we have a subset not containing n, we just put n in it. So subset not containing n is a a subset of the numbers 1 through n minus 1. And then this is a subset of n actually containing n. Well, it's not exactly the bijection we want. That shows that the number of subsets containing n equals the number of subsets not containing n. Those are in bijective correspondence. But actually the same bijective correspondence proves what we want to. Now in each such pair, S with n added to it, one of these subsets has odd cardinality and the other one has even cardinality. Now since there's 2 to the n subsets altogether, we have 2 to the n divided by 2 pairs, or 2 to the n minus 1 pairs. Each pair has exactly one even component and one odd component. So each of them, so there's exactly 2 to the n minus 1 even subsets and 2 to the n minus 1 odd subsets. They line up perfectly. Alright, now I want to look at another bijective proof that also involves binomial coefficients. Let's let A be an n by n matrix. With n squared distinct entries. And the number of distinct square submatrices of A, including the 0 by 0 empty submatrix, is 2n choose n. So we'll count the k by k submatrices as k goes from 0 to n. So this is the sum of n choose k times n choose k as k goes from 0 to n, where we can think of the first n choose k as choosing k rows to use. And we can think of the second n choose k as choosing k columns to use. Now with the columns, choosing k columns to use is the same as choosing n minus k columns not to use. So we're choosing k rows and n minus k columns not to use. Thus, from the set of n rows and n columns, 2n things, we're choosing k of the rows and n minus k columns, which is a total of n things. So we are choosing an n element subset of the set row 1 through row n, column 1 through column n, and there are 2n choose n ways to do this. So just as an example, here's a 5 by 5 matrix. Let's say we're choosing rows 2 and 4 and columns 3 and 4. This corresponds to choosing 2 and 4. Let me say row 2 and row 4. Column 1 not to use, column 2 not to use, and column 5 not to use. Which is a subset of row 1 through row 5, column 1 through column 5. So by thinking of the submatrix in a way that corresponds perfectly to n element subsets of 2n, we can see that this is the number of square submatrices of an n by n matrix. The end.